here we go. So we are on to the second half of our vectors unit. And it's still vectors, so we still talk about components, we still talk about vector resolution, but with the topics that we're going to cover, some of the applications have a different approach. And some people, I view these ones that we're going to do highly graphic. And so when people just show me a bunch of math and don't show me the picture that goes with it, there isn't full credit involved. Because the picture for these problems, if you understand how to interpret it, tells you exactly what to do. So we have three different categories, well, it's not three different categories, two specific categories. One today that we're going to call, that we're discuss, that's called statics. There is the application of an inclined plane that uses vectors. And then the third one, which is super bland, is just there are general vector questions that if you can draw the picture right and you can see in the picture that, oh, I got to do this vector stuff with the stuff that's in the picture, that's how you figure out the answer. So we're starting with statics. And some books will refer to this as equilibrium, and you will even hear the term static equilibrium. They all mean the same thing. But from a vector perspective, they have one theme in common. The sum of all of your vectors in an equilibrium or a statics problem equals 0. Now I do want to see if you, because we've played with vectors graphically, where if I said, hey, here are 4 vectors, add them together graphically, and you have to get out the protractor and the ruler, connect them tip to tail, and all that kind of stuff. If I told you I have 4 vectors that I want you to graphically add together meticulously, but the circumstance is an equilibrium situation, can you tell me what's going to happen when you add those 4 together graphically on your paper?
There would be no resultant because it would end at the beginning.
Perfect. And for people going, end at the beginning, what the hell you mean? If you've added vectors tip to tail, you know exactly what that refers to. You're just like drawing this thing, and then you get to the very last one, you measure the direction, you go to draw the right length, and it would connect right back to where the tail of the very first vector you drew. And so the other way of thinking of this is my resultant equals 0. Now on a kind of a more broken down level, this also means that when you are in a statics or an equilibrium problem, that the horizontal and the vertical components all have to add up to 0, because that's the only way that you can get a resultant of 0. Yes? This is because we don't know how many vectors there are. So this is like, you know when you do sigmas and you have an official beginning and ending? Like if we did sigma n equals 1 to 4, and I did that, then we would have V1, V2, V3, V4. I don't have like an ending. If I wanted to be really meticulous, we would have something like that. You know, it goes on as long as it needs to. So that's what the N refers to. Okay, so we are going to try and work through a couple problems because I view these concepts more not so much just go memorize a bunch of equations as draw the picture the right way and then make connections in the picture, and you can set up the math that will give you the answer that you're looking for, because different problems will flow differently. So this is not as equation based as it is draw a picture and then figure figure something out about that picture. Now, most of the statics problems we're going to deal with do involve forces. So when I say draw the picture and it involves forces, anybody remember the name of the forces picture you draw? What they called it? The free body diagram. So the idea is draw your picture and just start to put arrows on it where you think they belong. Okay, so let's start with a really simple example. I have a 10-kilogram object that's just hanging on a cable. And we go, how is that a statics problem? It's just hanging on a cable. It's just sitting there. What's the FA on my cable? And if this was asked in a word problem format, they'd probably use the word tension. But I hate when people use tension because then people just run to a book and say, where's the equation? Tension is just a kind of a cable or rope form of FA. So I prefer the FA thing. How many people already know the answer? Okay, what is it?
Positive 9.8.
Ooh, close.
Negative 9.8.
No, you were closer on the first one.
Other 10.
No.
Oh,
Okay,
that's
why
right.
98? What was the 10 missing?
1,000.
It's
The
math-
10 was missing, well, I got to multiply by 9.8.
Wait,
Your
it's math
9.8 was,
integration.
oh, I got to multiply by the 10. Because
Yeah.
in order for you to figure this out, what F do you have to first find?
Wait.
You have to find FW. And that's M times G.
Yeah.
And that would give us a negative 98 because in this problem we are meticulous about up is positive, down is negative. So that gives me a negative 98, which means if this thing is just sitting there, this has to be equal and opposite to that. Okay? Now, if we were to draw this as a vector problem, what would it look like?
Oh.
It's like a line with an arrow, like 2 arrows on it.
Okay? Which let's say we started with this one. What would it be? What would it look like?
Like put another arrow but pointing upward.
Yeah, we're just going to do it here. If this is our FW, what arrow would it be? Which way would it point?
Down.
Down. And we'd say, okay, that's my FW. What then would I do for my FA?
Like an
Trace.
upward pointing thing on the same line.
Yeah, if someone said, well, you got to change colors, I'd have to say, well, can I just put it like right next to it? Because it's basically overlapping that. And it's going to be just as big up as this is long down. And people say, that's a stupid picture. It's just like 2 arrows opposite direction slapped on top of each other. That's what it is. Okay? Now, mathematically, what we ended up saying here was that FA plus FW had to equal 0. And because we could figure out FW as negative 98, that allows us to play with that equation to come up with, well, FA must be positive 98. All right? Now, so mathematically simple, it's kind of almost dumb. But we're going to do the same thing in the problem that we're going to look at today, which is number 20. But when we go here, we are not going to be in 1 dimension. We are going to open it up to 2 dimensions. And when we're done with number 20, painstakingly done, I've officially assigned you 2 additional ones, 19 and 31. 31 is really similar to 20. 19 deviates in terms of the picture, but if you know how to handle the picture, you should still end up going to that and going, okay, this isn't too bad, as long as you work with the picture properly. So, we are just going to start with number 20.
Mr. Penovich?
Yeah,
Just kind of a quick question.
yeah.
Is tension just when like 2 opposite forces are reacting on like a rope or like pulling on it?
I want to say, I think it would be more correct to say that tension is whenever you have, or the more common thing is, tension is when you have a force being transmitted through a cable or a rope. So it's, and the idea is that there is things acting in both directions, but it kind of depends, it can become complex because if the object is actually moving, then the tension may, like in the last problem, wow, the tension is equal but opposite to the weight. When things are actually being allowed to accelerate or move, that can go, that simple equal but opposite thing kind of goes away.
Okay.
And that's the part where I always get irritated when people just go and like memorize equations, because really if you break the situation down with a free body diagram, you could figure out, you know, does the tension go up compared to weight or down compared to weight depending on what's happening in the problem.
Okay.
Okay, so here's our picture, and I think they give us 100, right? Yeah. 100 newtons. And we are supposed to figure out what is the tension in the two wires. Now, I am referring to this as wire number 1 and wire number 2. Okay, so the first thing that I need to do here is draw a free body diagram. Now, some people might say, draw the free body diagram over here on the side that mimics what's happening in the physical situation here. I kind of like to slap my free body diagrams on top of the picture itself, just because I'm more comfortable doing that. So what could I add in this picture to start to put the free body diagram in here? This is the part where people are like,
Downwards arrow.
Okay, we could start by saying, I'm going to put a downward arrow for, and specifically, what are you thinking when you say put the downward arrow? What are you?
Gravity.
Okay.
Weight.
So, and you mentioned weight, so I could do that. Now, if I was going to put, well, actually, I'll come back number-wise. What else could I put in here? There are two different things that could go in here right now. I think one of them makes more sense to most people than others. This thing's just hanging here, right?
An
So-
upwards arrow.
Okay. How big is that now? How big does that upward arrow have to be?
Equal to FW.
Okay. So I'm going to put this like that. Now, I'm not, depending on how you process this, this is the one that I'm not sure if people would go here first. Is there anything, like when you look at this and go, hey, where does that come from? Is there anything physical in the picture there that you would say, oh my God, I see the thing that it comes from?
From the ropes.
Well, okay. Now some people will say, well, they come from the ropes. But which way do the ropes pull?
Down. I guess. They're pulling up on the object.
Why, if we think really meticulously about vectors, why might I say, hey, you're kind of right, but not completely right? Which way does this wire pull?
Sideways.
It pulls, yeah, sideways at an angle.
Oh.
It actually, I'm going to do this in a different, oh, we are really getting colors in here. It pulls that way.
Oh, okay.
Which way does this one pull? This is the visual thing where people,
The other way.
all right? Oh, and I'm going to do something here. And I want you to critique me. Okay? Is that a good job?
No, it's too big.
Why is it too big?
They should both be equal
Why?
because they're both equal length and the same angle.
Okay, the biggest thing will be the angle. Because of the symmetry in this picture, this thing is going to pull just as hard as this. Now, when people go, how are you supposed to know that? Like, I don't know. But there's symmetry in the picture. So that means, even though some people say, well, you're going to do this mathematically, so who cares about the graphical aspect of it? I kind of understand that, but there's a reason why I'm going to try and do this more meticulously. So, what I'm going to do is I'm actually going to, I think that's about the same. So they should be about the same if you were trying to graphically show things accurately. Now, this guy here, because it's a tension, it's an applied force, so I'm going to call it FA1, because that's the tension for wire number 1. And I'll call this FA2. Now we'll put some numbers in here. They already said they only put this as 100, but if we're being really meticulous, what am I going to add when I start to talk about this mathematically? Picky.
100. Oh,
If I do this, it's like, not really.
negative.
Negative.
Oh,
And when you're like, hey, why didn't they put the negative in there? They usually do not do that when they just talk about the weight of an object. You could say that's cheesy for them to do, understood, but they do. So now, let's see, where do we want to go from here? All right. The 2 in orange, people tend to say, oh, I'm okay with that because I see a wire there. But we have an equal but opposite. So how big would this one be?
positive 100.
This is positive 100. So we have positive 100 newtons acting upward. But when someone goes, where the hell does that come from? Because there is nothing physical right there above the object. Now, if somebody says, well, they're the wires that are pulling up. We just finished saying, they don't pull exactly up. They pull to the side. So how do you get an upward thing from this? And this is where I'll bring up, I'm not going to bust out the protractor and the ruler here, but if we were to try and draw things meticulously, if I take FA1, I think that's pretty good. And I add FA2, it's a little long. It's actually, I don't think I did a good job on the angle there. Got a little tall. Between these two, if this is my FA2, and I then say, hey, I'm going to add these two together. I draw my resultant. There is my resultant. So that's where this thing comes from. I don't have to have a physical thing there, but I do have 100 newtons acting perfectly upward to balance this. Okay? Yeah.
Could you take FA1 and that's the hypotenuse and then you
No.
Okay.
Not, you're headed in the right direction. Because when the question asks, how much tension is there in the 2 wires? We haven't even addressed that yet. But this is where the conceptual side of vectors come into play. This is a 2-dimensional problem. What are our 2 dimensions here?
Vertical and horizontal.
Okay, and so if I said, draw me a frame of reference for your 2 dimensions being vertical and horizontal, what would it really look like from math? It would look like a, and we would say horizontal, vertical, or X, Y. Either one of those works. I have a term, I call them problem vectors. Remember when we were adding when we were adding vectors together graphically, we expressed them in polar coordinates. Point it the right way, draw it the right length, connect things tip to tail, you're all good. But that's a pain in the butt. But we said you can't do regular math with vectors in polar coordinates. We can only do math with things that are perfectly horizontal or vertical. So anything that is not perfectly horizontal or vertical, I call them problem vectors, because I can't leave them the way they are. Now, how did we get around that when you think of just generally adding vectors like we did in the mathematical vector assignment? How did we get around that? What did we do to a vector when it was a problem vector? Which technically they all were, because none of the ones I gave you were perfectly horizontal or vertical.
You found X and Y.
Right.
vectors.
What did we call that? What are you doing to the vector when you're finding the X and Y piece? Our word,
Resolve.
you're resolving it.
Oh.
So when I look at this picture, I have three vectors in my problem. The red one and the two orange ones. Two of them are problem vectors, the orange ones. So in order to do this, in my head, I have to say, I need to resolve those. So how do we resolve them, Anthony?
You make
Graphically. What am I going to do to this, add to this picture, so that I can then say, oh, I can work with that?
like across the bottom and then upwards.
Okay? What can we call this then?
FA1X,
Okay? And this one?
FA150.
Okay? What about over here?
The same thing.
How is it kind of the
The
same,
X
but
is negative.
okay, so from here, and then this becomes FA2X, FA2Y. Okay? Now, once we do this, can we put some numbers in here? Where?
FA1Y.
Okay, now before we get there, because you're going next step, what about inside the triangle?
40 degrees on the left side.
Okay, this is the 40, and then most classes have done this, but I'm like, hey, that's good enough. But many have said, oh, and that's 50. I'm like, all right, that's fine. But now the big deal is what? Where you were headed?
The FA1Y is 50 newtons.
Okay, what do you think the most common wrong answer was?
100.
100. And if someone said, oh, see, 100, you got the 100, you're balanced, what would you then point out to them?
There's 2.
There's two of them. And remember, we talked about the symmetry in the picture. Now, this is where I will go ahead and tell you, if you ever get a test question like this, guess what you will not get? You will not get the same angle. So you're not going to be able to make that assumption. But you can still work with this, because remember, all your X stuff and all your Y stuff has to add up to 0. So with this being 50, that means we know this is 50. Now what? What's our goal?
Find FA1 and FA2.
Which is what in the triangle?
The hypotenuse.
The hypotenuse. So if I'm going to come over here and say, all right, it's time to blow this thing up. So what do we do? I'm just going to finish this off in black. Okay.
You can use tangent to find FA1X.
Okay.
Like tangent 40 degrees equals 50 newtons over FA1x.
Okay, and then what would you do?
And then once you have FA1x, you can just do the Pythagorean theorem.
Okay, you could. Quicker way?
Oh, just use sine.
Opposite is going to be our 50 newtons, and hypotenuse. If you saw this differently and you got fixated on this 50-degree thing there, what would the other thing be that you could use if you were using this angle as your reference angle?
Cosine.
You'd use cosine of 50 degrees, because the cosine of 50 degrees is exactly the same as the sine of 40 degrees, and you would have 50 over FA1. Okay? Now, FA1x, FA2x have to be equal and opposite, but they never even asked us for do. So they didn't ask us to do that, so we don't have to. So this is my thing about these problems. When people don't show me their picture, you're not getting full credit, because the picture helps you set up the math, okay, or make the connection. Okay, that's good. So with this one, as an example, number 31, very similar, but it kind of flows differently. They do have a symmetric nature to that picture. And number 19 is not like this at all. But if you draw the picture, and remember this idea that because the thing in the picture is just sitting there, all of the x pieces have to add up to 0 and all the y pieces have to add up to 0. That should help you. Yeah.
So on the test ones where it might be asymmetrical, the idea is that it's just the same thing, but you can't say it's the same tension in each wire. You have
Right.
to
The
just solve
tension
two
will not be the
triangles.
same. But in this picture, what two things, if this was not symmetric, which two things still have to be equal and opposite then?
The downwards and upwards force.
Correct. The red and the green,
Yeah, the weight.
but there's something else that you would have to connect with first before you could go into the vertical dimension.
Oh, the force on each wire is still the same.
Well, these are not the same. The FA1, FA2.
Oh yeah.
What two arrows in here still have to be equal but opposite, even if these are not the same angle?
FAX1 and FAX2.
This one and this one. So this is where you would actually have to target these first. And if you're going, why the hell do I need to do that? You need to do that because you can't do this. Oh, I got equal, they're equally supported vertically on both sides. That's out the window. But they are equally supported horizontally, because if these two weren't balanced, what would it be doing?
Like it would lean to.
It would have to be actively moving that direction.
Um,
This is the cool thing. If someone goes, oh yeah, it'll lean to one side. When it leans to one side, what that ends up doing is adjusting these two, which ends up adjusting the size on these two until they end up balancing out. You won't have to worry about that. Yes,
What are those two arrows in this one? Like how do you?
I don't know. They don't ask for them, so we never find out what they are unless you really want to. Crazy.
Okay.
Okay? Any questions on this? Okay. Day one of statics.